Welcome back. I'm doing this problem here about a car, a 1500 kilogram car that's driving and then there is the force of drag on the car, and they ask, let me just redraw it, or re-describe the problem. You have a car and it's moving this way, so if it's moving this way, then there is a drag force that's backward, and they say the area of the car that's facing is 1.4 by 1.6. So that means the area is 1.4 times 1.6. They give us the drag coefficient, it's 0.35, and then they say, as the car moves, at what speed will the drag force equal to the rolling friction force? So first of all, let me just draw the car as just a box here. So here is the car, like so, and it looks like a box. And the car moves this way. The forces on it are, this is not a force, this is the motion, speed, V. There is a normal force, there is mg, and then there is the force of drag, and then there is the force of rolling friction, And I know that in the y direction there is no motion, it means that the normal force is equal to mg. I know that the rolling friction, Fr, is equal to mu r, the coefficient of rolling friction, times the normal force, and so the rolling friction is mu r times m times g. It's a car that's rolling on asphalt or concrete, and so the coefficient of rolling friction, and I actually have a typo here, this should say r, rolling friction. Rubber on concrete, 0.02, so I would use this. Rubber on concrete is, mu r is 0.02. I know the mass, it's a 1500 kilogram car, gravity is 9.8, so I have this. Now, I would like the drag force to equal to this one in magnitude. So I want the force of drag to equal to the force of rolling friction. The force of drag is 1/2 the drag coefficient times the density of the air times the area of the car, density, area, speed squared, and that has to equal to the force of rolling friction, and that's equal to mu r times m times g. I would like the speed, so v, you solve for it, so it would be 2 mu r m g divided by c rho a, and you square root this whole thing. Okay, so let's plug in the numbers and see what we get. So we get 2, mu r is 0.02, we said, 0.02 for the rolling friction. The mass of the car is 1500 kilograms, gravity is 9.8, and C. Drag coefficient is 0.35, that's given to us. The density of air is 1.3, about it's 1.29, 1.3. What's the area? The area is 1.4 by 1.6, so 1.4 times 1.6 times 1.6. Well, let's multiply and see what we get. We get 2 times 0.02 times 1500 times 9.8 over 0.35 over 1.3 over 1.4 over 1.6, and you square root that, and I get 24 meters per second. Which is, I forget how many miles an hour. We can look it up always. So about 24 meters per second, about 50 miles per hour. 50 miles per hour. Okay. So that's one problem. Now, as you know, if something drops, the more it speeds, the more drag there is. The more drag there is. And so, let's say somebody is like an air diver, or what do you call them? Air diver? Skydiver? Skydivers. And they drop, and the question is, when would they reach terminal speed? Meaning, at what speed will they be moving so that they will be moving at constant speed? So let me just describe it. So let's say a typical person is 75 kilograms, and let's see what we get. So let me go to the next. All right, so here's the problem for the terminal speed. So let's say you have a person, skydiver, and the person is falling. So first of all, what kind of shape does the person have? So as the person falls, we're kind of long, so we can model ourselves as a cylinder. So here's the person. Like a cylinder, like so. Here's the person. And the person is falling, so they're falling this way. And we looked at a cylinder earlier, we said C is approximately 0.35 for a cylinder. So as the person falls, what are the forces involved? Well, the person is on Earth, so there has to be gravity downward. There has to be the force of gravity. And it is equal to mg. Now the person doesn't just fall freely, there is the drag. And the drag is in the upward direction, the force of drag. Of course, when the person jumps at first, their speed is 0, and as they fall, they gain speed. But then the faster they go, the more drag they will experience, although gravity will still be basically the same. And so this drag force, which is equal to 1/2 C rho A V squared. C is constant, the density of air is approximately constant, the cross-sectional area of the person is fairly constant. If you open your arms, you can increase your surface area, but you can have some maximum surface area. If you have a parachute, that'll be nice because it has a very broad area, so the drag will be much. Let's say if you have an area as a person, let's say you're, I don't know, maybe 1.5 square meters. But then if you have a parachute, let's say it's 10 square meters, so there'll be much more drag. So as they fall, this drag force will increase, and at some point the drag force will equal to the mg, and once they are equal, it means the net force is equal to 0, and the speed will just be constant, and that's called the terminal speed. They will reach some maximum speed, and it would be called the terminal speed. So at some point, I will write here, at some point, at some velocity, the drag force will equal to mg. So this one is upward, this one is downward. If you like, drag force minus mg equal to 0, so the drag force will equal to mg. So what would the speed at that time be? Well, let's write down. The drag force is 1/2 rho C A V squared equals to mg. And let's solve for v. So we get v will equal to 2 mg divided by rho C A square root. Alright, so now we have to make some assumptions. 2 is 2. What's the mass of the person? Well, I don't know. It depends on the person. So let's say 75 kilograms. Gravity, 9.8. Over. Density of air, that's 1.3. C. We said the person is approximately like a cylinder, like a log, and so that's 0.35. Typically, what would an area of a person be? Well, we're about half a meter this way, and if we're 2 meters this way, so 2 times half a meter, 0.75, that will give you about a meter, so maybe like a meter, 1.25 meters, give or take. So let me just be generous and hit 1.3 meters, square meters. It depends, obviously. So you run the numbers, and let me get my calculator here. So I have 2 times 75 times 9.8 over 1.3 over 0.35 over 1.3, and take this to the 1/2 power. I get about 50 meters per second. 50 meters per second. 49, 50. Let me just double check, make sure I didn't get a ridiculously large number. Yeah, I actually got a much larger number than they did, because as it falls as a cylinder like that, the coefficient here is 1.1. Is 1.1. 1.1. So 1.1. We would like the drag speed, the terminal speed, you would like it to be smaller, because it's less deadly. So 38 meters per second, or, I mean, that's still high. That's about 90 miles an hour. That's still kind of large. 90 miles an hour. Imagine if you just fall without the parachute, you would hit the ground at 90 miles an hour. That's deadly. Okay. I think that looks good. We made reasonable assumptions and so on. And so we have maybe 3 problems in this chapter, and then we will do the end of chapter problems, some practice. All right, so here's an example that I would like to go over. So you have a car, a 1,500 kilogram car is traveling at a speed of 30 meters per second when the driver slams on the brakes and skids to a halt, meaning driver slams on the brakes, so the wheels lock. So the wheels lock. So if the wheels lock, the car will just skid. So there is relative motion between the rubber and the concrete. And we'll assume the concrete is dry, so we can use, it would be kinetic friction, rubber and concrete. If it's dry, that's about 0.8. So the car skids to a halt. So now they would like us to calculate the stopping distance if the car is traveling up a 10-degree slope, B, down a 10-degree slope, and then we can add C if it's a level road. So let's do these 2 first, and then we will maybe consider C. So let's say the driver is traveling up a road, traveling up. So here is the incline. Let's say the car is going up the incline. So this is the motion. So what are the forces involved? The forces involved will include the force of gravity, mg. And so mg will have 2 components. There will be an mg mg sine theta this way, and an mg cosine theta, and an mg sine theta. This mg can break down to these 2. And then there is the normal force, as usual. Now, since the car is moving upward and skidding, so if it's skidding, remember, friction always opposes the motion, so there will be force of friction in what direction? Always opposes the motion, so it's this way. That's called the force of friction, and in this case it's kinetic friction, because the car is skidding. Is there anything else? The answer is no, because there is no force pushing the car upward. The car just has some speed, and eventually it will come to rest. It will come to rest somewhere here. This will be x initial, that's 0. X final is some distance. Okay? And as usual, we'll take this to be the x direction and the perpendicular to the incline to be the y direction. So in the y direction, the net force is equal to 0 because the car doesn't leave the incline, doesn't go into the incline, just moves along the incline. So the normal force minus mg cosine theta will equal to 0, so the normal force is equal to mg cosine theta. So I'll skip that step. So we get, using the sum of the forces in the y direction equal to 0, we get the normal force equal to mg times the cosine of theta. That means the force of kinetic friction will equal to mu k times the normal force, mu k times the normal force, but the normal force is mg cosine theta. So it's mg cosine theta. So now, the net force in the x direction will equal to the mass times acceleration in the x direction. So I have the net force. The net force in the x direction will equal to the mass times the acceleration in the x direction. I'll just call it ma. The forces in the x direction, you get the force of friction, but it's negative because it's downward, so it's negative mu k mg cosine theta, so it's negative mu k mg cosine theta. And then there is the mg sine theta. It's also down the incline. We assumed up the incline to be the positive x direction, so this is negative, so it's also negative mg sine theta. Are there any other forces in the x direction? The answer is no. So that's equal to the mass times acceleration, ma. Notice the mass does not matter. And so we get that the acceleration is equal to negative. I would factor the minus sign. I would factor the g also. G. And what's left? I would have mu k cosine theta. Mu k cosine theta plus what? If you take the minus sign, you take the g, you just have the sine of theta. And so let's calculate the acceleration. Plug in the numbers. We would plug in theta equal to, what's the incline angle? It's a 10-degree slope, so it's 10 degrees. So theta is 10 degrees, and mu k is, I'll put it here, mu k, I'm assuming it's 0.8. So put in your calculator here, g is 9.8, so let's see. So we got sine of 10 plus 0.8 times the cosine of 10 times 9.8, and so we get negative 9.42, negative 9.42 meters per second squared. So how far will it go before stopping? Well, initially it's moving at 30, and so we will use the fact that we're still in part A. So we'll say V final squared minus V initial squared is equal to 2 times the acceleration times x final minus x initial. Minus x initial. This is the distance that it has moved. And so we get V final will be 0 because the car stops. V initial is 30, and 30 squared is 900, so 900 equals to 2. The acceleration is negative 9.42 times d. And so we get the stop, the distance will be, so let's multiply this by 2. So the car will stop in about 48 meters, 47.75. And put 47.8. So the car will stop in about 48 meters, 47.8, if it's going up the incline. As you would imagine, if the car is going down the incline and slams on the brakes, well, being down the incline doesn't help you stop quicker. So it will stop. It will make you stop in a longer distance. So let's do that part. do that part. Let's see here. Where's my chart? Love to do it with this. So let me draw my same thing here. So now the car is heading down the incline. So here is the car. The car is going downward at a speed. This is part B. Yeah, part B. The initial speed is 30 meters per second. So, what are the forces involved? Well, if the car is moving downward, first of all you got mg, and mg breaks down into an mg cosine theta, and then mg sine theta this way. There is of course the normal force, and then there is the force of friction, and it's up the incline, because if you're sliding down the incline, the force of friction will oppose the motion, and it's up the incline. Okay. So we say the net force in the y direction is 0. There is no motion that way, and so the normal force is equal to mg cosine theta, as before. Normal force is equal to mg cosine theta, and so the force of friction is mu k times the normal force, and so it's equal to mu k times mg cosine theta. And so now we will look at the x direction. Again, here is the plus x, here is the plus y. So the net force in the x direction equal to the mass times acceleration in the x direction. So I get, what are the forces in the x direction? You got the mg sine theta, it's in the positive x direction, and the force of friction up the incline, so that's the negative x direction by our coordinate choice, and that equals to the mass times the acceleration. So I have mg sine theta minus the force of kinetic friction, that's mu k mg cosine theta equals to ma. The mass goes away, and so the acceleration is equal to factor the g, so you get g times the sine of theta minus mu k times the cosine of theta, and let's calculate that. We plug in, it's still the same coefficient of friction because it's the same car, the same tires, the same road, so it's 0.8, and the angle is 10 degrees, so let's plug it in. So get sine of 10 minus 0.8 times the cosine of 10 times 9.8. So that gives you negative 6.02 meters per second squared. That makes a lot of sense. It's negative. If positive is down the incline, the acceleration is up the incline, meaning it's opposite to the velocity. That's how you slow down. And so we'll use exactly the same formula, and so we'll say v final squared minus v initial squared is equal to 2 times the acceleration times x final minus x initial, that's just d. Call it the stopping distance. And so we get b is equal to v final squared minus v initial squared, that's 0 minus 30 squared is 900, divided by 2a, 2 times the acceleration, that's negative 6.02, and we get 900 over 6.02 over 2, 74.75, so 74.8 meters. So an extra, what, 30 meters or so? 30 meters that you need to stop because of the down the incline. It's harder to stop. You see that when you went up the incline, the acceleration was negative 9.42, but down the incline was a smaller acceleration, so you slow down at a smaller rate. Okay, so let's get to the next example. And actually, before I go to the next example, let me do the flat case where it's if there is no slope. just to have exhausted everything. If there is no slope, here's the car. Let's say the car is moving this way, and let's say that's the positive x direction. This is the y direction. The forces are, you get the normal force, you get the mg, and if the car is moving this way, there is the force of kinetic friction. Notice now, if it's horizontal, the mg is just straight down. It does not have the component along the incline. So the normal force is simply equal to mg in this case, because the angle is 0 degrees. If you put normal force is mg cosine theta. If theta is 0, cosine of 0 is 1, so the normal force is mg, as it should. So the normal force is mg, and so the force of kinetic friction is mu k times the normal force, so it's mu k times mg. And so we say the net force in the x direction equal to the mass times acceleration. So the net force in the x direction will equal to the mass times the acceleration in the x direction. But the net force in the x direction is the force of kinetic friction, and it's negative. So negative the force of friction, which is negative mu k mg, and that equals to the mass times acceleration. So the mass cancels, and so the acceleration will equal to negative mu k, which is 0.8, I think. Yeah, mu k was 0.8 times gravity, which is 9.8. And so I expect it to be not as quickly stopping, the acceleration not as large as the one up the incline, but not as small as the one going down the incline. So somewhere between -9 and minus 9.4 and -6. You might say it's halfway through. I don't know if it's exactly halfway through. Actually, I'll be curious. So let's see, 0.8 times 9.8, that's 7.84. So negative 7.84 meters per second squared. Okay. In fact, let me average these two, and I'm just curious. 9.42 plus 6.02 over 2, that's 7.72. Yeah, almost halfway between them. Anyway, so that's the calculation. And so the distance, it would be exactly like this formula. So D would be V final squared, that's 0, minus V initial squared, that's 30 squared, which is 900, divided by twice the acceleration, which is 2 times negative 7.84. And so we get, 900 over 2 over 7.84, and about 57.4 meters. That's how long it would take it to stop. Okay. And so that's that one. So in the next video, I'll do 2 more problems, and that will be the end of chapter 6. And then we will do maybe 1 or 2 more videos on the practice problems, okay, from the end of the chapter.